Okay, so in this video, I'm going to go over proof of the Cantor, Schroeder, Bernstein theorem. And I'm going to go over a proof that has a particularly nice visual interpretation accompanying it. Um, so let's see. So let's state the theorem. It's usually abbreviated as the CSV theorem. And the idea is that given two sets X and Y, if there is an injective set F from X to Y, and if there's an injective set from Y to X, so they're both injective, then there is a bijection between X and Y, like this. Okay, now usually the proofs are notoriously difficult. They're not mind-blowingly advanced, but they're pretty elementary. But having to follow them takes a bit of time. Um, so let's see if we can simplify this. Okay, so I'm going to start with the visual representation, and I'm going to depict the set X by a square. I'm going to depict Y by a circle. So, since by hypothesis there's an injection F from X to Y, we can imagine a kind of embedding that takes the square X and embeds it in the circle Y, like this. And this is done by the function F. Now, likewise, there is another mapping, G, that's also injective. And it embeds the circle Y into the square X, like this. But now we know the square X is embedded in the circle Y, so there's going to be a sub-embedding of the square inside the embedded circle, like this. And we can see, so in this case, f of x is a subset of y. And in this case, this is done by the function g of f of x is a subset of x. Okay. Now the trick is that let us define a composition, a composition function h g of f from x to x. And what it does is just as what we've seen, it just you take the function f and then you follow it up by taking the function g. And so in one iteration, we have this square with a circle inside, but then we know there's a square inside the circle, and this inner square is created by the function h. But then there's another circle inside, and that has its own square inside, and it's again created by the function h, like this. And we can go on ad infinitum, like so. Okay, but now what this does is it divides up the original set x into subparts in a very interesting way. And the way it does it is now we have um, parts of X that are in the outer square, but not in the first circle. And then there's parts in the first circle, but not in the first inner square, and so on. And so we can color those regions appropriately. Okay, let's see. So I'm starting with X. I'm going to try to embed this circle. Okay, it goes like so. And now we can color it with various colors. So I'm going to color the outer region red. Then I'm going to color second square, or the first inner square, is orange. Now let's see, let's move on to yellow. Let's try gray. And I'm gonna color the circular parts that are not in the next square as blue. Okay, and now I'm gonna call this piece P1. I'm gonna call this piece P2. So the red one is P1, the orange one is P2, the yellow one is P3, the gray one is P4, and so forth, like this. Now some other things are in order. I'll define z naught as the set x, and then inductively zn plus 1 as the set h of zn. Then I'll define w naught equals g of y, and then inductively the set wn plus 1 will be h of wn, like so. And then with these, I can rigorously define p then to be the set zn set minus wn, like this. Okay, great. Now comes the main trick. And the main trick here is that we want to be able to establish a bijection between x, which is the large square, and y, which is the large circle. And the way we're going to do this visually is we're going to take the red region, and using the function h, we're going to move p1 to p2, so the red into the orange, and then the orange to the yellow, so p2 to p3, then the yellow to the gray, so p3 to p4, while keeping the blue regions intact. So what we're going to do is we're going to define a function k from x to w naught, which is just g of y, by k of x equals h of x if x is in some p sub n, and we're going to leave it as x otherwise, like so. Great. So this is the set. We have this depiction. As I explained, red goes into the orange region, orange goes into the yellow region, then the yellow goes into the gray region, and so on. And so we've managed to create what I claim is a bijection between x and the set G of y, and then uh, since G is injective, uh, there's a bijection between the set y and G of y, and so if we can establish a bijection between x and G of y, it's enough to establish a bijection between x and y itself, because G of y and y are bijective already. Um, So it only remains to prove that K is a bijection, and from this case, from this visual representation, it's already apparent that it must be bijective, but in order to be rigorous, we can go over this directly. So first, we're gonna go over and ask, is K injective? And so suppose K of x equals K of x prime. And there's three cases to consider. Case one is x is in P of m, and x prime is in P of n, where n, so they're both in some set, some, they're both in one of the sets P, in one of the P sets. Um, but then we have h of x is h of x prime, and h is injective, so it follows that x equals x prime. Case 2. Case 2 is that x is not in any of the sets Pm, but x prime is in one of the sets Pn. Okay, by definition of h, we know that x is some element, it's in the image of h, so h of x prime, ah, that's right. So we defined k to be h of x if x is in P of n, and otherwise it's just x otherwise. So in this case, let's see, x is not in P of m, so it just stays. And then k of x prime reduces to h of x prime. So that's how we got this equation. And in such a case, let me see. Well, h is injective, so it's, let's see, p h of p of n, that was defined as Zn set minus Wn, that equals h of Zn set minus h of Wn. That was defined as Zn plus 1 set minus Wn plus 1, and that equals p of n plus 1 by definition. And this assumes h is injective. Okay, but that means x is in Pn plus 1, which is a contradiction because we assumed it's not in any set Pm for any Pm, for any M. Okay, so that means case 2 is impossible, and we need not worry about it. There's one more case left. So there's also a variant of 2 in which the roles of x and x prime are switched, but that is essentially identical to case 2. So we'll not have to concern ourselves with it. The only real remaining case is case 3, and that's when both x is not in any PM and x prime is not in any Pn for all Mn. But then, just going to the definition of K, that just implies, let's see, by a direct reading of how K is defined, that just immediately implies that x equals x prime. And so in all cases that are possible, we conclude that if K of x equals K of x prime, then in all cases that are possible, x equals x prime. Great. And that proves that uh, K is injective. Great. Now we want to prove that K is surjective. Let's see. So take some elements x and g of y, which is in the codomain of K, and there are two cases to consider. So case 1, x is not in Pn for all n. But then again, by direct reading of K, that just means K of x equals x. So it's in the image of K. So that's simple. And now case 2 is that x is in some set Pn for some n. Now this requires a bit of thinking. Note that first of all, since P naught is x set minus g of y, we can't have n equal to 0, so n is not equal to 0 here, because x is within the set g of y. Okay, so instead, n has to be greater than 0. Next, note that as we've established earlier, somewhere here, right here, it's actually the case that P of n is h of P of n minus 1. And so if x is in P of n, x has to equal, and n is greater than 0, x has to equal h of y for some y, for some y in P of n minus 1. But then by definition of K, that just means x equals K of y, and so x is again within the image of K. And so this covers all two possible cases. Thus, K is surjective, and thus the function K, this function K, written here, is indeed bijective, establishing a bijection between x and g of y as we desired. And that completes the proof of the Cantor, Schroeder, Bernstein theorem. There we go. Okay.